The enthalpy of evaporation is also known as the latent heat and is referred to as H sub Fg. This is the amount of heat required to change the state of water at its boiling temperature into steam. It involves no change in the temperature of the steam-water mixture. All the energy is used to change the state from liquid, so water, to vapor, saturated steam, as seen here. The old term latent heat is based on the fact that although heat was added, there was no change in temperature. However, the accepted term is now enthalpy of evaporation. Like the phase change from ice to water, the process of evaporation is also reversible. The same amount of heat that produced the steam is released back to its surroundings during condensation, when steam meets any surface at a lower temperature. This may be regarded as the useful portion of heat in the steam for heating purposes, as it is that portion of the total heat in the steam that is extracted when the steam condenses back to water. The enthalpy of saturated steam is the total energy in saturated steam, and is simply the sum of the enthalpy of water and the enthalpy of evaporation, as seen here. In this equation, the term H sub G is the total enthalpy of saturated steam. H sub F is the liquid enthalpy, or the water enthalpy, also known as sensible heat. And H sub Fg is the enthalpy of evaporation, as it was discussed in the previous video. Recall, the old term for the enthalpy of evaporation is latent heat. The enthalpy, as well as other thermodynamic properties of saturated steam, can easily be referenced using the tabulated results of water and steam experiments, known as steam tables. This will be discussed further ahead in the next video. The steam tables list the properties of steam at varying pressures. They are the results of actual tests carried out on steam. The following table shows the properties of dry saturated steam at atmospheric pressure. At atmospheric pressure, so a gauge pressure of 0 bar, water boils at 100 degrees Celsius. And as seen in a previous video, 419 kilojoule of energy are required to heat 1 kilogram of water from 0 degrees Celsius to its saturation temperature of 100 degrees Celsius. Therefore, the specific enthalpy of water at atmospheric pressure and 100 degrees Celsius is 419 kilojoule per kilogram, as shown in the steam tables. Another 2,257 kilojoule of energy are required to evaporate 1 kilogram of water at 100 degrees Celsius into 1 kilogram of steam at 100 degrees Celsius. Therefore, at atmospheric pressure, the specific enthalpy of evaporation is 2,257 kilojoule per kilogram, as shown in the steam tables. This also means that at atmospheric pressure, the total enthalpy of saturated steam is 419 plus 2,257, so 2,676 kilojoule per kilogram at atmospheric pressure. This is also shown on the steam tables. However, keep in mind steam at atmospheric pressure is of limited practical use. This is because it cannot be conveyed under its own pressure along a steam pipe to the point of use. Now, because of the pressure-volume relationship of steam, where volume is reduced as pressure is increased, steam is usually generated in the boiler at a pressure of at least 7 bar gauge. The generation of steam at higher pressures enables the steam distribution pipes to be kept to a reasonable size. This will be discussed in the sizing section of the course. As the steam pressure increases, the density of the steam will also increase. As the specific volume is inversely related to the density, the specific volume will therefore decrease with increasing pressure. The following figure shows the relationship of specific volume to pressure. This highlights that the greatest change in specific volume occurs at lower pressures, while at the higher end of the pressure scale, there is much less change in specific volume. The following extract from the steam tables shows specific volume and other data related to saturated steam. Note here that at 7 bar, the saturation temperature of water is 170 degrees Celsius. More heat energy is required to raise its temperature to saturation point at 7 bar than would be needed if the water were at atmospheric pressure. The table gives a value of 721 kilojoule to raise 1 kilogram of water from 0 degrees Celsius to its saturation temperature of 170 degrees Celsius at 7 bar gauge, versus 419 kilojoule to raise 1 kilogram of water from 0 degrees Celsius to its saturation temperature of 100 degrees Celsius at atmospheric pressure. It is also important to note here that the enthalpy of evaporation needed by the water at 7 bar to change it into steam is actually less than the heat energy required at atmospheric pressure. So 2048 versus 2257. This is because the specific enthalpy of evaporation decreases as the steam pressure increases. However, as the specific volume also decreases with increasing pressure, the amount of heat energy transferred in the same volume actually increases with steam pressure. Steam with a temperature equal to the boiling point at that pressure is known as dry saturated steam. However, to produce 100% dry steam in an industrial boiler is rarely possible, and the steam will usually contain droplets of water. In practice, because of turbulence and splashing, as bubbles of steam break through the water surface, the steam space contains a mixture of water droplets and steam. Steam produced in any type of boiler where the heat is supplied only to the water and where the steam remains in contact with the water surface may typically contain around 5% water by mass. If the water content of the steam is 5% by mass, then the steam is said to be 95% dry, and therefore has a dryness fraction of 0.95. The actual enthalpy of evaporation of wet steam is the product of the dryness fraction and the specific enthalpy from the steam tables, as seen here. It is important to note that since the dryness fraction of wet steam is a value less than unity, then wet steam will always have lower usable heat energy than dry saturated steam. As a result, and from this equation, the actual total enthalpy of wet steam would be as follows. Because the specific volume of water is several orders of magnitude lower than that of steam, the droplets of water in wet steam will occupy negligible space. Therefore, the specific volume of wet steam will be less than dry steam. The actual specific volume is given by the following equation, where V sub G is the specific volume of dry saturated steam. To better illustrate these concepts, let's refer back to the steam table. Now, steam at a gauge pressure of 6 bar, having a dryness fraction of 0.94, will only contain 94% of the enthalpy of evaporation of dry saturated steam at 6 bar gauge. The calculations that will follow use figures from the steam table.